everyone. In this video, I'm going to use the 1D mechanical translational library to build a system. I'll bring in the components that I need, and my goal here is to model what would typically be seen as a 2-cart, 3-spring system where you have fixed ends and you want to analyze the system to get the natural frequencies. So I'll bring in all the components that I need, connect everything together, and then what I'm going to do is I'm going to add some parameters, and I'll just make them all common between them. So meaning the same mass for both objects, the same spring stiffnesses, just to keep it simple. So I'll do K for my spring stiffness. I'll give it a default value of 10. And then I'll have an unstretched length called L0 that will also be common for all my springs. So go back to my model, and I need to set these parameters. So I'll select all my springs, give those parameters, select my masses. Notice that we have a length of 0 for our masses. Now I need to initialize everything in the correct position. So this first mass should be at 1 unstretched spring length. The second one will be 2 unstretched spring lengths away. And this is measured from this left point here. Finally, this right point, we'll just make it 3 unstretched spring lengths away. And to make sure that I've kind of positioned and set everything up correctly, I'm going to add these probes and run a simulation. What I'm expecting is that mass 1 is at 0.2, mass 2 is at 0.4, and nothing is moving. So that's what we see here in the plots. So that's great, everything is initialized correctly. Now what I want to do is I want to add an actuation to my system, so I'll add this force component, connect it to my first mass, and then I'll just search here for a sign, and I'll connect all of this together. Maybe just make this a little bit smaller. And then we can see whether or not this is actuating everything correctly. We should see the masses moving in our results manager. So this, open it up, great. So now the next step is really to go and get the equations for the system so that we can then continue our analysis. So I'm going to go to my apps and templates under model analysis and equation extraction. I'm going to connect to my model. And then I'm going to be able to change names of variables and parameters just to give them, names that maybe make a bit more sense. So in this case, I'll call my position x1 and my velocity v1. Just naming that's going to be more common if you're looking in a dynamics textbook or other resources. v2, and then we'll go to parameters. And what we'll do here is we'll change our mass to just be m, toggle it to be symbolic. What this is going to do is it's going to force it to stay in the equations that I extract instead of substituting in the numeric value. And actually, the last one I'm going to do here is this is actually my force, so I'm going to rename this to F. All right, so now I can extract my equations, and just to be explicit, I do care about the ODEs. So we see our equations here. What's very handy in the apps is it actually gives me the code that's being executed behind the scenes. So that I could actually reproduce this. So I'm going to copy this, go here and attach a worksheet. This is going to be a Maple worksheet where I can not only connect to my system, but I can also use any of the packages in Maple. So I copy this, I run it, and I should get the exact same results, which I do here. So I can see my differential equations. So that's great. Just close these up. And now I can start doing analyses. So what I really care about doing is some kind of a dynamic analysis. There is an entire package for this. In this case, I do have differential equations. I will convert these to ODEs. If I actually go to the help here, right, I can see that my ODEs or my DEs have to be a list, and there's different options and explanations here. So I'll convert these on the fly to a list, define my inputs, and define the outputs that I'm interested in. So using that nice names that I used in the app previously. So now I have a dynamic system, and once I have this set up, I can actually do things like Bode plots without too much effort. I just need to specify some parameter values, because remember I did keep things symbolic. I'll use the same values that I had put in my parameter block, and we'll run this. Oh, and we see here it is, this is I put 1, 0 instead of L0. So I get my magnitude plot, my phase plot, but maybe I don't want both of these. Maybe I also don't want this logarithmic. So I'm just going to add some different options. Again, these are all things that are in the help. So I'll define a linear frequency range, define the range to be an area that I'm more interested in. Number of points, I'll increase this just to make it look nice. And for the output, I'll just care about the magnitude plot. So now we will have kind of a higher resolution plot. And really what we want to figure out is what are expressions for these natural frequencies. So we are expecting 2 of them, which makes sense. This is a 2 degree of freedom system. So now I can actually do some other commands. So dynamic systems does have a characteristic polynomial function. So I'll call this on my system. And I actually see that it tells me that my system needs to be a specific type, which is state space. So first I'll actually just convert my system. So I just call the dynamic systems package again, state space, and I just call it on the original system. And Maple will just automatically convert this for me. So now I can actually run, I need to change this to state space, and it actually gives me my characteristic polynomial. I do need to modify this because this is in the S domain, I need it in a frequency domain. So I'm going to make a substitution. It's going to be I times omega. I here is the imaginary number. Right, so now we're working in frequencies, kind of the frequency domain. The next thing I'll do is I will substitute omega squared for lambda, just a variable to kind of make solving a bit cleaner. So square root of lambda, I'll sub this back into the characteristic polynomial. Great, so now we're in a position where we can solve. So we'll find the lambda solutions, and we'll solve for a characteristic polynomial in terms of lambda. So we get 2 frequencies, so that's great. And then we'll do one last calculation just to get the natural frequencies represented in radians per second. So we're going to do square root, and we're just going to apply this on a list of the lambda solutions. So now we're going to get 2 results. So our first one is root k over m. The second one is root 3k over m. So this agrees with, if you look up in a textbook or an online resource, these are the results for the natural frequencies. And then of course we can substitute in the values we used previously, so k being 10, m being 1, into the natural frequencies, and we can see that we get 3.16 and 5.47, which if we look at our plot here, that does correspond with these peaks that we're seeing, so 3.16 and now here 5.47. So this is how we're able to actually graphically see results, analytically get results, also symbolically, which is very important. And now we can actually return to our MapleSim model, and we can change this frequency. So we'll change it to radians per second. And for the first test, we'll just do square root of k over m, so that first natural frequency, and we'll run a simulation. Now, because it's a natural frequency, we are expecting those displacements to grow with time. And indeed, that's what we see here. And maybe one last thing that we can do is we'll create a new plot, and we will add this here. And we can see that both masses are actually moving in sync. So if you were to visualize this, those objects going left and right in unison, and that's our natural frequency. That's our fundamental mode. Again, if we maybe increase this to 2 times k over m, so now we're not at a natural frequency of the system, so we're not expecting any kind of growth in the results. So it's just going to be some kind of chaotic result, right? So we see that there's no real growth in the amplitude. And then finally, we'll go back and we'll actually just put 3 times k over m, which is our second natural frequency. So again, we should see some growth in the displacement or the position of these masses. And then of course, what's different here is we see that when one mass is moving to the right, the other one is moving to the left, and they're moving opposite. So of course, you're getting, they're moving in opposite directions back and forth. And that's what we expect for the second mode. So this was just a bit of an overview on how you can actually create a simple model, get the equations, perform additional analysis in Maple, and actually come back and use those results to investigate your model and run it. Thanks.